November 11th, 1944, Manchuria, Japanese-occupied China. Captain Mikhail Zhivkov of the Soviet Air Defense Forces stared at the massive silver aircraft sitting intact on the frozen runway at Vladivostok. The Boeing B-29 Superfortress, forced down after bombing runs over Japan, represented technology the Soviet Union desperately wanted. What Zhivkov didn't know was that 2,400 miles away in Tokyo, Japanese military engineers were staring at photographs of another captured B-29 with identical hunger and far more desperation. The Japanese had managed what seemed impossible. They had captured a nearly intact B-29, the most advanced bomber in the world, a flying fortress that had been systematically destroying their cities. Japanese engineers believed they could reverse engineer this American marvel, copy its sophisticated systems, and turn America's technological advantage against them. They had the blueprints written in aluminum and steel. They had captured engines. They had detailed photographs and measurements of every component. What they didn't have, what they would never achieve despite desperate efforts, was the industrial capacity to replicate what American factories produced by the thousands. The story of Japan's attempt to copy the B-29 Superfortress reveals the brutal mathematics of industrial warfare, where desire and determination collided with the immutable reality of manufacturing capability. It's the story of how Japan discovered that capturing advanced technology meant nothing when you lacked the industrial infrastructure to reproduce it. The Boeing B-29 Superfortress represented the pinnacle of 1940s aviation technology. When it first flew on September 21, 1942, it was unlike anything that had come before. At 99 feet long with a 141-foot wingspan, it dwarfed previous American bombers. But size was the least impressive aspect of this technological marvel. The B-29 featured a pressurized cabin, allowing crews to operate at 30,000 feet without oxygen masks, far above most fighter interception altitude. Its four Wright R3350 duplex Cyclone engines, each producing 2,200 horsepower, gave it a top speed of 365 miles per hour and a range of 3,250 miles fully loaded. The aircraft could carry 20,000 pounds of bombs across vast distances, deliver them with unprecedented accuracy using the sophisticated Norden bomb sight, and return home. Remote-controlled gun turrets represented revolutionary technology. Instead of manually aiming guns exposed to slipstream and temperature extremes, gunners sat in pressurized compartments, controlling weapons through a centralized fire control system. The B-29 carried 12 50-caliber machine guns and one 20mm cannon, creating defensive firepower that could shred attacking fighters. The cost reflected its sophistication. Each B-29 cost approximately $639,000 in 1944 dollars, equivalent to roughly $10 million today. The entire B-29 program cost $3 billion, more than the Manhattan Project. America would build 3,970 B-29s during the war, a production feat that itself demonstrated industrial capacity beyond Japanese comprehension. The first B-29 raid on Japan occurred on June 15, 1944, launched from bases in China targeting the Imperial Iron and Steel Works at Yawata. The psychological impact exceeded the physical damage. For the first time since the Doolittle raid in 1942, American bombers struck the Japanese homeland. But unlike Doolittle's token attack, the B-29s represented sustained strategic bombing that would only intensify. Japanese air defense commanders initially believed they could counter the B-29 threat. The Nakajima Ki-84 Hayate fighter, entering service in 1944, could theoretically reach B-29 operating altitudes. Japanese pilots were experienced and motivated. Anti-aircraft defenses around major cities were formidable. But the B-29's combination of altitude, speed, and defensive firepower proved devastating. Japanese fighters struggled to reach 30,000 feet, and those that did found their engines gasping for oxygen at that altitude. The B-29's speed at altitude matched or exceeded most Japanese fighters. Attacking the superfortress meant penetrating concentrated 50 caliber machine gun fire from remote-controlled turrets that tracked targets with alarming precision. By October 1944, B-29s were flying regular missions from the Mariana Islands, newly captured American bases that put Tokyo within range. General Curtis LeMay was developing tactics that would transform strategic bombing. The Japanese needed answers, desperately. The opportunity came on November 1, 1944. B-29 number 42-24622, nicknamed Ding Hao, took off from Chengdu, China, on a mission to bomb the Omura aircraft factory on Kyushu. The superfortress, piloted by Captain Howard Jarrell, encountered mechanical problems after the bombing run. With engines failing and fuel running low, Jarrell realized he couldn't reach friendly territory. Soviet territory was closer. Stalin had declared neutrality in the Pacific War, maintaining diplomatic relations with Japan while fighting Germany. Jarrell made the calculated decision to land at Vladivostok, hoping Soviet neutrality meant internment rather than death. The Soviets interned the crew, but seized the aircraft with undisguised enthusiasm. Stalin immediately recognized what his engineers were telling him. The B-29 represented technology the Soviet Union desperately needed. He ordered the aircraft studied, measured, copied. What followed was one of history's most ambitious reverse engineering projects, resulting in the Tupolev Tu-4, an almost exact copy of the B-29 that would fly in 1947. But the Soviets had something Japan lacked: industrial infrastructure capable of supporting such copying. While Soviet engineers struggled but ultimately succeeded, Japanese engineers would attempt the impossible and fail spectacularly. The Japanese capture of B-29 components occurred through different circumstances. Multiple B-29s were shot down over Japan or crashed in the Pacific. While most sank, Japanese forces recovered engines, instruments, and structural components from several crashes. In July 1945, as the war entered its final month, Japanese engineers had accumulated enough B-29 components to attempt reverse engineering. The Technical Air Armament Department of the Imperial Japanese Army Air Force, located in Tachikawa outside Tokyo, received orders to analyze captured B-29 technology and determine if Japanese industry could replicate it. What they discovered would shatter any remaining illusions about Japan's technological competitiveness. The team was led by several of Japan's most accomplished aviation engineers. Among them was Takeo Doi, who had designed the Mitsubishi A6M0 fighter. These men understood aircraft design at the highest level. They approached the B-29 with professional respect and growing desperation. Japan needed a bomber capable of striking American bases. The B-29 design offered a potential solution if they could copy it. They began with structural analysis. The B-29's aluminum alloy airframe used 7075 aluminum, a high-strength alloy developed by Alcoa. Japanese metallurgy couldn't produce equivalent alloys. Their aluminum was softer, heavier, and less resistant to stress. Building a B-29 airframe with Japanese aluminum would require either accepting reduced strength or increasing weight significantly, which would destroy the aircraft's performance characteristics. The engineers calculated that substituting Japanese aluminum would increase empty weight by approximately 8,000 pounds, reducing range by over 30% and ceiling by at least 5,000 feet. This eliminated the B-29's primary advantages: long range and high altitude capability. But the structural challenge was minor compared to the power plant problem. The Wright R3350 duplex cyclone engine represented American engineering at its absolute peak. This 18-cylinder twin-row radial engine produced 2,200 horsepower continuously, could sustain that output for hours, and achieved this while maintaining reasonable fuel consumption and mechanical reliability. Japanese engineers completely disassembled a captured R3350, measuring every component, analyzing every system. What they found was both impressive and impossible to replicate. The engine contained approximately 10,000 individual parts, manufactured to tolerances measured in thousandths of an inch. The crankshaft alone, forged from special steel alloys, represented manufacturing capability Japan simply didn't possess. The supercharger system used precision-machined turbine blades that required specialized metallurgy and manufacturing processes. The fuel injection system incorporated components with tolerances and reliability standards Japan had never achieved. Even the spark plugs, seemingly simple components, were manufactured to specifications Japanese industry couldn't match. Major Yoshiro Takano, assigned to analyze the R3350, wrote in his report, "The American engine represents manufacturing standards we cannot achieve with current Japanese industrial capability. Each component reflects precision manufacturing, quality materials, and design integration beyond our current abilities. Attempting to copy this engine would require completely restructuring Japanese aircraft engine production, and even then, success is uncertain." The most powerful Japanese aircraft engine in production was the Nakajima Ha-45, powering the Ki-84 fighter. This 18-cylinder engine produced 1,990 horsepower, impressive for Japanese engineering, but still 200 horsepower short of the R3350. More critically, the Ha-45's reliability was questionable. Engines frequently failed after 100 hours of operation. The R3350 was designed for 750-hour overhaul intervals and often exceeded that. Japanese engineers attempted to design an engine matching the R3350's specifications. The Nakajima Ha-505 project aimed to produce 2,200 horsepower using 18 cylinders in a twin-row radial configuration. Engineers worked frantically, but the Ha-505 existed only on paper when the war ended. Even if completed, there's no evidence it would have achieved American reliability standards. The fundamental problem was manufacturing infrastructure. American aircraft engine factories used precision machine tools produced by companies like Cincinnati Milling Machine and Brown and Sharp. These tools could hold tolerances of 0.0001 inches across production runs of thousands of components. Japanese machine tools, many produced domestically with inferior materials, couldn't match this precision consistently. Quality control represented another insurmountable gap. American aircraft engine production involved systematic inspection using precision measuring instruments. Statistical process control, pioneered in American manufacturing, ensured consistent quality across production runs. Japanese manufacturing relied more on skilled craftsmen compensating for inadequate tooling through individual expertise. This approach worked for limited production, but couldn't scale to mass production of complex engines. Materials science formed the foundation of the capability gap. The R3350's cylinder heads used aluminum alloy castings with embedded steel valve seats. The process required metallurgical expertise and quality control that Japanese foundries had never mastered. American alloy steels used in crankshafts, connecting rods, and other stressed components came from electric arc furnaces that produced consistent, high-quality steel. Japanese steel production, heavily damaged by American bombing and constrained by resource shortages, couldn't match American steel quality. Even seemingly simple components revealed the gap. The R3350's piston rings required precise dimensional control and surface hardening. American manufacturers could produce millions of piston rings with consistent quality. Japanese manufacturers struggled to produce them in adequate quantities with acceptable quality. The supercharger represented particular challenges. American turbo superchargers used in B-17 and B-24s and the mechanical superchargers in the R3350 required turbine blades manufactured from heat-resistant alloys. These blades operated at temperatures and stresses that would destroy ordinary steel. Japanese metallurgy had developed some heat-resistant alloys, but nothing approaching American capabilities. Fuel injection systems in the R3350 used precision-machined components with tolerances measured in 10,000ths of an inch. Japanese fuel injection technology existed, but was far less sophisticated. The reliability difference was stark. American fuel injection systems functioned flawlessly for hundreds of hours. Japanese systems required frequent adjustment and maintenance. Beyond individual components, system integration posed challenges Japanese engineers couldn't solve. The R3350 wasn't just 10,000 parts assembled together. It was an integrated system where each component was designed to work with others, where tolerances were calculated to ensure reliable operation under extreme conditions, where materials were selected based on comprehensive testing. American engineers at Wright Aeronautical had spent years developing the R3350, testing hundreds of prototypes, analyzing failures, improving designs. This iterative development process required resources, time, and industrial infrastructure that Japan, fighting for survival in 1944, simply didn't possess. Takeo Doi, examining the captured engine components, reportedly told his team, "We are looking at the product of an industrial civilization operating at peak efficiency. We could copy individual components, but we cannot copy the industrial system that produces them reliably. Without that system, we would build engines that look like the R3350, but fail catastrophically in operation." Japanese attempts to test-run captured R3350 engines revealed another problem: fuel quality. American aviation gasoline in 1944 was 100 octane, refined to exacting standards for consistent performance. Japanese aviation fuel was typically 87 to 92 octane and varied significantly in quality. The R3350, designed for high-octane fuel, performed poorly on Japanese gasoline and was prone to detonation that could destroy the engine. Even if Japanese engineers somehow built engines matching R3350 specifications, they couldn't produce the fuel those engines required. American petroleum refining used sophisticated catalytic cracking processes that Japanese refineries lacked. This created a cascading problem: inferior engines requiring inferior fuel, creating a performance deficit that couldn't be overcome. While engine challenges dominated engineering discussions, other B-29 systems posed similar problems. The remote-controlled gun turret system used electric motors, servo mechanisms, and fire control computers that represented technology Japanese industry had never produced. The General Electric fire control system in the B-29 used analog computers that calculated lead angles, coordinated multiple turrets, and allowed a single gunner to control multiple guns. Japanese engineers examining captured turret components found precision-machined gears, electric motors with consistent torque characteristics, and electrical systems with reliability Japanese industry couldn't achieve. The pressurization system, crucial for high-altitude operation, required precision seals, reliable pumps, and pressure regulation systems. Japanese aircraft had never been pressurized. Engineers had theoretical knowledge, but no practical experience manufacturing systems that could maintain 8,000-foot cabin pressure at 30,000-foot altitude while managing temperature extremes and preventing catastrophic failure. The Norden bombsight, America's most closely guarded bombing technology, incorporated optical systems, gyroscopic stabilization, and mechanical computing that calculated release points accounting for altitude, airspeed, wind, and ballistic trajectory. Japanese bombing technology was comparatively primitive, relying more on pilot skill than sophisticated equipment. Even seemingly mundane systems revealed the gap. The B-29's hydraulic system operated at 3,000 psi, far higher than Japanese aircraft hydraulics. This required precision-machined pumps, high-pressure seals, and quality hydraulic fluid. The electrical system used standardized 28-volt DC power, with generators capable of sustained high output. Japanese aircraft electrical systems were less sophisticated and less reliable. Radio equipment in the B-29 included VHF communications, radar warning receivers, and navigation aids. American electronics manufacturing had advanced rapidly during the war, producing reliable, compact equipment. Japanese radio technology lagged significantly, with equipment that was heavier, less reliable, and less capable. The instrumentation panel in the B-29 contained gauges and indicators for monitoring dozens of systems. American instrument manufacturing produced reliable, accurate gauges consistently. Japanese instruments were less precise and less reliable, requiring pilots to compensate through experience and skill. By August 1945, Japanese engineers had compiled comprehensive reports on their reverse engineering attempts. The conclusion was unambiguous. Japan could not replicate the B-29 with available industrial capacity. Individual components might be copied, but system integration was impossible. Even if somehow assembled, the resulting aircraft would be so inferior to the original as to be operationally useless. The report estimated that building even a simplified copy would require redirecting the entire Japanese aircraft industry for at least 2 years, assuming no American interference. Given that American bombing was systematically destroying Japanese industry, this timeline was fantasy. Moreover, the simplified copy would lack the performance characteristics that made the B-29 effective: high altitude, long range, heavy payload, and defensive armament. The engineers recommended abandoning attempts to copy the B-29 and instead focusing on developing interceptors capable of destroying it. This led to projects like the Nakajima Kika, Japan's jet aircraft program, and the Mitsubishi Ki-83, a high-altitude interceptor. But these programs started too late with insufficient resources, produced only prototypes before Japan's surrender. The contrast with Soviet success in copying the B-29 reveals the importance of industrial infrastructure. Stalin assigned the Tupolev Design Bureau to reverse engineer captured B-29s. Soviet engineers faced similar challenges to their Japanese counterparts, but the Soviet Union possessed something Japan lacked: intact, heavy industry capable of producing the necessary components. Soviet factories could produce aluminum alloys approaching American quality. Soviet engine manufacturers, though struggling, eventually replicated the R-3350 as the Shvetsov ASH-73. The process took years and required diverting massive resources, but Soviet industrial capacity could sustain the effort. Soviet aviation benefited from Lend-Lease technology transfer during the war, giving engineers exposure to American manufacturing methods. Even with these advantages, the Soviet Tu-4 program took until 1947 to produce a flying aircraft, and even then, Soviet copies never achieved the reliability of American originals. The Shvetsov ASH-73 engine, despite being an almost exact copy of the R-3350, required more frequent overhauls and had higher failure rates. If the Soviet Union, with superior industrial infrastructure and more time, barely succeeded, Japan's failure was inevitable. Japanese industry in 1945 was collapsing under American bombing. Factories were destroyed, supply chains were disrupted, resources were exhausted. Attempting to reverse engineer the B-29 under these conditions was like trying to build a skyscraper during an earthquake. The industrial statistics tell the story starkly. In 1944, at the peak of Japanese war production, Japan manufactured approximately 28,000 aircraft total, all types. The United States produced 96,318 aircraft that same year, including 3,627 B-29s. American aircraft production alone was more than 3 times Japanese production, and this doesn't account for tanks, ships, vehicles, and weapons, where American advantages were similar or greater. The engine production gap was even more dramatic. Wright Aeronautical's single plant in New Jersey produced more R3350 engines monthly than all Japanese engine manufacturers combined produced in all types. American engine production benefited from specialized machine tools, standardized manufacturing processes, and quality control systems that Japanese industry couldn't replicate. American Alcoa aluminum production in 1944 exceeded 1.5 million tons. Japanese aluminum production peaked at approximately 150,000 tons annually. This 10-to-1 disadvantage in a critical material meant Japan simply couldn't build aircraft at American rates, even setting aside quality differences. The machine tool gap was perhaps most critical. American machine tool manufacturers produced precision equipment that enabled mass production of complex components. Companies like Cincinnati Milling Machine, Brown and Sharp, and Pratt and Whitney Tool Company produced equipment capable of holding tolerances that Japanese manufacturers could barely measure, let alone achieve consistently. Japanese machine tools were adequate for pre-war production requirements, but inadequate for wartime mass production of advanced weapons. Many Japanese machine tools were worn out from overuse, lacked proper maintenance, and couldn't be replaced because machine tool production had been neglected in favor of weapons production. Quality control represented another dimension of the industrial gap. American manufacturers used systematic inspection, statistical process control, and standardized testing procedures. Japanese manufacturing relied more heavily on skilled craftsmen who could compensate for inadequate equipment through individual expertise. This approach works for limited production, but cannot scale to mass production. The engineers attempting to reverse engineer the B-29 understood they were confronting not just technical challenges, but fundamental industrial realities. The B-29 wasn't just an advanced aircraft. It was the product of an advanced industrial civilization operating at maximum capacity. Every component reflected manufacturing capabilities, material science, quality control, and system integration that required decades of industrial development. Takeo Doi's final report, submitted days before Japan's surrender, concluded, "The B-29 represents industrial achievement beyond current Japanese capabilities. We could build an aircraft that resembles a B-29, but it would not be a B-29. It would lack the performance, reliability, and capability that make the American bomber effective." The gap between Japanese and American industry, revealed by this analysis, is so large that closing it would require fundamental restructuring of our entire industrial base, a process requiring decades under peacetime conditions. Under wartime conditions, with our industry under systematic attack, closing this gap is impossible. The attempted reverse engineering of the B-29 revealed uncomfortable truths about industrial warfare. In total war between industrialized nations, manufacturing capacity matters more than individual courage or tactical brilliance. The side that can produce more weapons of better quality more reliably will eventually win. Technology can be captured, designs can be copied, but industrial infrastructure cannot be quickly replicated. Japan's inability to copy the B-29 was symptomatic of larger strategic failures. The decision to attack the United States in 1941 assumed American industrial potential wouldn't matter in a short war. Japanese strategic planning assumed American decadence and lack of fighting spirit would lead to negotiated peace before industrial mobilization became decisive. This assumption was catastrophically wrong. Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack, understood American industrial potential. He reportedly said, "I can run wild for 6 months, but after that, I have no expectation of success." His timeline proved remarkably accurate. By mid-1942, American industrial mobilization was beginning to tip the balance. By 1944, when Japanese engineers examined the B-29, American industrial dominance was absolute. The B-29 itself represented American industrial strategy. Rather than incremental improvements to existing designs, American planners invested massively in revolutionary technology. The B-29 program cost more than any other weapons program except the atomic bomb, a staggering commitment that paid enormous dividends. By 1945, B-29s were systematically destroying Japanese cities, mining harbors, and preparing for the invasion that never came because atomic weapons ended the war first. Japanese attempts to develop equivalent technology always lagged. The Nakajima G-10N Fugaku, a proposed heavy bomber matching B-29 capability, never progressed beyond design studies. Resources were unavailable, and even if built, Japanese industry couldn't have produced them in meaningful numbers. The Fugaku remained paper dreams, while B-29s burned Japanese cities. The psychological impact of the B-29 on Japanese leadership was profound. Prior to 1944, Japanese civilians had been largely sheltered from war's reality. The B-29 changed that, bringing war directly to the home islands. The inability to stop the raids, despite desperate efforts, demonstrated to Japanese leaders that they had lost control of the war. Emperor Hirohito's decision to surrender after the atomic bombings was partly influenced by the systematic destruction B-29s had inflicted. By August 1945, Japanese cities were burning, industry was shattered, and starvation threatened. The B-29 had done its job, supported by an industrial base Japan could never match. Post-war analysis by both American and Japanese historians confirmed what the engineers discovered in 1945. Japan never had realistic chances of matching American industrial production. The resource base, industrial infrastructure, technological expertise, and organizational capacity simply didn't exist. Japan's empire provided raw materials, but lacked the industrial plant to convert those materials into weapons at rates approaching American production. Some historians argue Japan should have recognized these limitations before starting the war. Others note that Japanese leadership understood the industrial gap, but hoped for a short war, where initial successes would force negotiated peace. Both perspectives agree that by 1944, continuing the war was hopeless, yet Japanese leadership fought on, perhaps because acknowledging the industrial reality meant admitting the entire war had been a catastrophic mistake. The captured B-29 components that Japanese engineers studied now reside in museums, testimony to an attempt that was doomed before it began. The Wright R-3350 engine sits in the Yamato Museum in Kure, a monument to American industrial achievement and Japanese inability to replicate it. Veterans of the reverse engineering project who survived the war spoke rarely about their work. Takeo Doi, in a 1962 interview, reflected, "We were skilled engineers attempting an impossible task. We understood aircraft design, but the B-29 taught us that in modern war, engineering excellence means nothing without industrial capacity to implement designs." America didn't just build better aircraft, they built better factories. That was the war's real lesson. The Soviet Union's successful copying of the B-29 as the Tu-4, while initially impressive, ultimately demonstrated the limits of reverse engineering. The Tu-4 served Soviet purposes but was quickly superseded by indigenous designs. Copying teaches you how something was done, not necessarily how to do it better. Innovation requires more than replication. The B-29 program demonstrated American willingness to invest massively in technology development. The $3 billion spent exceeded many nations' entire military budgets. This investment philosophy, which continues in modern American weapons programs, reflects belief that technological superiority can be purchased through massive R&D investment. The B-29 validated that philosophy. From Japanese perspective, the failed attempt to copy the B-29 represented something more profound than a technical failure. It represented the moment when Japanese engineers confronted the full reality of the industrial gap that had doomed their nation's war effort from the beginning. Every measurement taken, every component analyzed, every material tested revealed capabilities Japan simply didn't possess and couldn't develop in wartime. The experience influenced post-war Japanese industrial development. Engineers who had seen American manufacturing capabilities firsthand became advocates for industrial modernization. Post-war Japan would adopt American manufacturing techniques, quality control methods, and process standardization, eventually building industries that competed successfully with American manufacturers. But in 1945, those developments were decades away. In the ruins of Japanese cities burned by B-29s, Japanese engineers filed reports documenting their failure to replicate American technology. The captured engines, instruments, and components were studied one last time, then stored as the war ended and American occupation began. General Curtis LeMay, who commanded the B-29 bombing campaign, later reflected on Japanese attempts to copy the superfortress. They captured the aircraft, but they couldn't capture the industrial base that built it. That was the real weapon, not the B-29 itself, but the thousands of factories, millions of workers, and integrated industrial system that produced it. You can't reverse engineer that. The attempted reverse engineering of the B-29 stands as one of history's great what-if scenarios. What if Japan had possessed the industrial capacity to copy the superfortress? Could Japanese B-29s have struck American bases? The answer is almost certainly no, because the industrial capacity required to copy the B-29 would have fundamentally changed Japan's entire warfighting capability from the beginning. A Japan capable of building B-29s would have been a different Japan, with different strategic options, perhaps making different decisions. The mathematics were inexorable. American industry in 1944 was producing one B-29 every hour at peak production. Japanese industry, attempting to replicate a single example, concluded they could not do so with available resources. This wasn't a temporary setback or a solvable problem. It was fundamental industrial reality asserting itself over military necessity. The story resonates because it reveals technology's true nature in modern warfare. Advanced weapons don't win wars by themselves. They must be produced in sufficient quantities, supported by adequate logistics, operated by trained personnel, and maintained by robust supply chains. Capturing one example of advanced technology provides knowledge, but not capability. Capability requires the industrial ecosystem that produces the technology reliably and in quantity. The Japanese engineers who disassembled the Wright R3350 engine understood what they were seeing. A precision-manufactured product of an industrial civilization operating at a level Japan had never achieved. Each component, each system, each integration point represented manufacturing capabilities that couldn't be quickly replicated or easily transferred. Modern analysts studying this episode note its relevance to contemporary technology competition. Nations today attempting to copy advanced weapon systems face similar challenges to those Japanese engineers confronted in 1945. Technology can be observed, measured, even replicated in isolated cases, but systematic production requires infrastructure that takes decades to develop. The B-29 reverse engineering failure teaches that in industrial warfare, the factory matters more than the weapon. The industrial system that produces reliable, complex weapons consistently is more valuable than any single weapon system. American victory in World War II owed more to Detroit, Pittsburgh, and countless other industrial centers than to any particular weapon or battle. The captured B-29 that Japanese engineers studied represented not just an aircraft, but an entire industrial civilization's output. Every precision-machined component, every sophisticated system, every integrated feature reflected capabilities Japan could observe, but not replicate. The engine that Japanese engineers called impossible to copy had been produced by the thousands in American factories, installed in aircraft that rolled off assembly lines at unprecedented rates. By war's end, 3,970 B-29s had been built. Japan had captured perhaps a dozen engines and various components from downed aircraft. They studied these artifacts intensively, learning everything they could. Yet that knowledge couldn't bridge the industrial gap. Information alone doesn't equal capability. The final irony came after Japan's surrender. American occupation forces found the reports Japanese engineers had compiled on the B-29. Reading these documents, American officials realized Japanese engineers had understood exactly what they faced. The reports were technically sophisticated, identifying capabilities and acknowledging limitations accurately. Japanese engineers weren't ignorant, they were simply trapped by industrial reality. Some captured engineers were interviewed by American technical intelligence. Their descriptions of Japanese attempts to replicate American technology provided valuable insights into both Japanese capabilities and limitations. These interviews confirmed that Japan's fundamental problem wasn't engineering knowledge, but industrial infrastructure. The Wright R3350 engine that Japanese engineers said was impossible to copy continued in production for decades after the war. Improved versions powered the Douglas DC-7 and Lockheed Constellation airliners. The engine's basic design proved so robust that derivatives were produced until the 1950s. This longevity reflected the soundness of American engineering and the quality of manufacturing that produced it. In museums today, B-29 superfortresses stand as monuments to American industrial achievement. The Enola Gay, which dropped the atomic bomb on Hiroshima, resides at the Smithsonian. Other examples are scattered across aviation museums worldwide. Japanese visitors studying these aircraft understand what their engineers discovered in 1945. This was technology their nation couldn't replicate when it mattered most. The captured engine components in Japanese museums carry their own lesson. They represent both technological achievement and the limits of technology transfer. Having the artifact doesn't mean having the capability. Understanding the design doesn't mean possessing the means to execute it. The story of Japan's failed attempt to copy the B-29 concludes not with dramatic failure, but with quiet acceptance of reality. Japanese engineers filed their reports, acknowledged the impossible gap, and recommended abandoning the effort. Their superiors, facing national catastrophe, could only accept these conclusions. The war ended before Japan could bridge the industrial divide that had doomed their reverse engineering attempts. In the ruins of Japanese cities destroyed by B-29s, among burned factories and shattered infrastructure, the captured engine components remained as testimony to what might have been and what could never be. Japan had captured the technology but could not replicate the industrial civilization that produced it. That distinction made all the difference between victory and defeat, between the possible and the impossible, between ambition and capability. The engineers who attempted this impossible task deserve recognition for their efforts. They worked diligently, analyzed thoroughly, and reported honestly about limitations they could not overcome. Their failure wasn't due to lack of skill or effort, but to mathematical reality. Japan's industrial base could not support what they attempted. Today, the story serves as a reminder that in modern technological competition, infrastructure matters more than information. Nations can steal secrets, copy designs, even build prototypes, but sustained production of advanced technology requires industrial ecosystems that take generations to develop. The B-29 wasn't just an aircraft. It was the product of American industrial civilization at its peak, and that civilization couldn't be copied by capturing one of its products. The Wright R3350 engine sits in its museum case, a monument to impossible dreams and industrial reality. Japanese engineers studied it, measured it, understood it, but could never build it. That engine, more than any battle or bombing raid, told the story of how Japan lost the war, facing an industrial power they could never match, attempting to copy technology their nation lacked the infrastructure to produce.